Billions and soon trillions in value will be created in the autonomy economy. By the time a trend becomes consensus, the alpha is already gone. The gap between uncovering signals and reading headlines is widening fast. When it's a headline, it's no longer a signal. Enter Autonomy AI. We decode signals before they move markets, giving you the edge while everyone else tries to decipher the autonomy economy. Autonomy AI. Your models, our intelligence. Visit AUTNMY.ai.
Kelly, you have an esteemed background from 13 years at NASA. That's cool. No, figuratively, you are a rocket scientist working on all forms of autonomy to go into space and eventually deep space. During your 13-year tenure at NASA, how did autonomy change and evolve?
Yeah, it's a great question, Grayson. Autonomy has actually been a core part of the lifeblood of NASA's human spaceflight operations since the very beginning. So a lot of those Mercury and Gemini and Apollo missions had a lot of automation already built into those systems. Now, the astronauts could take over if they needed to, but that's been a constant throughout. And for over the development of the Orion spacecraft, which just flew successfully to the moon and back on the Artemis II mission, autonomy was a huge part of that as well, making sure the astronauts were safe the entire time with a lot of levels of redundancy and protection and getting them safely back to Earth.
Would we be able to explore our solar system if it wasn't for autonomy?
You could, but it would be not very efficient. Um, Generally, you rely on those onboard autonomy systems to carry out tasks that enable you to do things that you otherwise can't do if you require direct real-time communication. A good, for instance, is when you're out at operating on Mars, the Earth to Mars distance is so long that it take many minutes for the commands that would be sent by presumably someone driving the rover on Earth to reach the vehicle. So it's an impractical form of doing that. So instead, what they do is they come up with a plan on the ground, they transmit up to the spacecraft, and then the spacecraft, whether it's a rover or a satellite, will go execute the plan autonomously. Of course, it has to monitor its own progress, making sure it doesn't have anything bad happen. If something bad happens, it needs to recognize that, stop, enter some sort of safe mode, and then send back the message back to Earth. So you can kind of think of it almost like writing a letter. It takes a while for that information to get there, process it, act on it, and then send back information of the results afterwards. So autonomy is kind of a key element of doing deep space exploration.
Years ago, I was fortunate to go on a NASA tour of JPL and saw the Mars rover and got to learn about the Mars rover program. And I remember way back when Time Magazine did a horrible thing. The Mars rover stuck. And what you're explaining, no, it's not stuck. It's sending back the data so it can get new coordinates. Is that in a situation that was very famously covered, such as the Mars rover, where it was stuck? Engineers at NASA then program, say, a new autonomy algorithm, send it up over that time it takes to get there, and then the rover, or in this case, the robot, will then go on its new journey, new mission?
Yeah, so in a nutshell, yeah, that's exactly what happens. Essentially, engineers operate on a time delay to see what the robot is able to see. They formulate a plan and send it to the robot. Now, the robot is going to try to follow the plan as best as it can, as it's been programmed by the engineers. Now, something that's been very exciting is recently there's been some recent advances in AI, and so my understanding is that JPL engineers have actually been able to get the Mars rovers, I believe it was Perseverance, to go operate entirely, essentially do the onboard mission planning entirely autonomously without having to rely on ground crew or essentially ground operations to support it. So I think there's some really exciting advances there. But yeah, in a nutshell, the spacecraft checks in, lets the ground know whether it's having problems, and if it needs help, then it'll request it.
Now, what's going to happen as the Artemis program evolves a very successful flight into the astronauts? Thank you for the great journey in the service to go up there and explore. The secretary has clearly stated, and the administrator, that we are going back to the moon along with the president. And looking at a lot of the documents that NASA has released for the planning, autonomy is going to play a very critical role in taking America back to the moon. How, from an engineering perspective, do you plan for that? Because there was, I forget the gentleman's name, but his last astronaut on the moon talked about the dust factor. He said that's there. And as we know from the ground vehicle perspective on Earth, not in space, dust plays a big role. How do you prepare for all those unknown elements in different environments?
That's a great question. It's a core element of NASA's approach is to do this kind of in a stepwise manner to kind of go and collect information as you go. You don't just go in one kind of potentially naive jump. You see this in the formulation of the Apollo missions that they progressively demonstrated new and better capabilities, and they learned the entire way they went. And so it's when they finally landed on the moon that's when they learned about the degree to which the lunar regolith or the lunar soil will electrostatically cling to all the surfaces and kind of gunk everything up, really abrasive on a lot of the mechanisms and mechanical things. So they learned that on their first mission when they landed. And so then now we have that knowledge, we carry that forward, and now we can address it in the future lunar exploration campaigns. But autonomy is going to play a massive role in it, in autonomously landing the spacecraft to get the astronauts down to the surface, autonomously lifting off, getting them back home safely, all the life support systems that are autonomous to make sure that pressure and oxygen and nitrogen are appropriately mixed using sensors and controlling valves. All that stuff is autonomous on board the spacecraft.
You had the experience working on the Orion spacecraft, and I'm curious. I know there's boosters in the Orions on the top, but are there different autonomy systems, let's say at launch going into orbit, and then different autonomy systems going when we're over 250,000 miles, then going down to the moon? Are those different systems? Are they intertwined? What does that look like from a technical autonomy perspective?
Yeah, that's a great question. Yeah, basically how you do solve the localization problem. Estimating
Mhm.
where is the spacecraft in outer space depends on where you are. So, what's the main source of gravity acting on you? Is it Earth or is it the Moon? Or are you kind of somewhere in between? What are the dominant forces on the spacecraft? You have to consider that. Uh, Additionally, the motion planning algorithms or the guidance systems, as it's known, those are varied too. And so, if you're doing a burn, that's a different guidance or a different motion planning system than coming in and doing reentry. And so, depending on the phase of flight, the onboard system will switch between different onboard planning modules, and it will also change what's the control system being used as well. Because depending on the phase of flight, whether you're in launch, the space launch system rocket, that's the thing that's controlling everything. And Orion is kind of a passenger on top that's kind of captive. Not until Orion fully separates from that rocket does it become in control of its own motion and orientation. And then, so it uses a set of thrusters to control it. So you need a separate control system for that. And then right before reentry, the capsule separates from its service module. And then the capsule comes in and reenters with its own control system using its own set of reaction control system jets. And so there's different control systems at every stage of flight, depending on the flight phase, different planning algorithms and different onboard navigation algorithms.
If you look at commercial aviation as a parallel, I've been fortunate. A major airline, I got to go see a teardown of an old 747 and meet some of the engineers. And the wires didn't cross, and the redundancy that was built in from a safety perspective, the wires not crossing, the different critical flight components being separated for safety reasons. Is that the same from the NASA perspective, where you have, say, the guidance algorithm that you worked on for Orion is in, I'll just be simplify it, in one box. The reentry algorithm is in another box, and then there's redundancy built into that because it's a life and death situation. It's not, you can't pull over to the side of the road, no pun intended.
Yeah, that's exactly right. NASA uses all of those redundancy principles, and it uses mixtures of patterns of safety architecture patterns. So, for instance, you think about what are all the things that can go wrong on a space mission. One of them, when you're far away from Earth, is that you might have bits in your computer get affected by radiation, and that can cause some of your memory to get corrupted, and that could cause you to do the wrong thing. So, to mitigate against that, the Orion spacecraft carries 4 primary flight computers. Gives you the ability to reject computers that go down, so you can have multiple computers go down without losing your entire primary autonomy system. Now, in the event that there is some common software defect that lives in all 4 of those because they're all running the same software, or some common hardware defect that would take them all out simultaneously, NASA developed a dissimilar backup flight software system that's ready to take over during critical flight phases, and that's known as the Orion backup flight software system.
The Orion backup flight software, because I'm just looking at distance, and obviously you have latency. There's not a fiber pipe going up to the Orion. Is that software physically in the capsule where the astronauts could activate it, or does that have to be uploaded?
Yeah, it's already installed on the spacecraft. In fact, on the little joystick that the astronauts can use when they're doing manual piloting, there's a little switch cover as if you're about to shoot a missile or something. You flip that up, you press a button, and it removes power to the primary flight computers, and you activate your backup flight software system. So if during a particular phase of the mission they don't like what the primary autonomy system is doing for whatever reason, they can flip that switch, hit the button, and engage the backup flight software and essentially regain control of the system.
With software, I'll use the NASA term, being mission critical to the success of the mission, how is it developed? How is it tested? How is it hardened? And the most important thing, because we have adversaries, how is it secured?
Oh, that's a great question. So NASA has its own software certification document. And so all the software that flies on Orion, for instance, falls under the category of what NASA calls Class A flight software. That's roughly equivalent to what in the automotive functional safety world you would call ASIL D, or in the aerospace, civilian aerospace called DAL A. And so basically what this really means is you have to have requirements for all of your capabilities. You have to trace those requirements to all the functionality that you actually go implement. You have to have 100% unit testing coverage when you're testing your code. And you need to have a defined software management process and how you're going to integrate all these things together, make sure that all the boxes are talking to each other, and then how you're going to verify that the overall system satisfies the system requirements. So there's a whole software community that follows these NASA standards to achieve incredibly high reliability rates. And how did these come about? It's because of past failures, frankly. So essentially, every time you have a new standard, it's usually because something went wrong at some point on a major mission, and we decided this is worth imposing this standard on everybody to make sure this never happens again. So what you've got is essentially 50, 60 years of collective wisdom of doing safety critical software engineering on spacecraft systems baked into the NASA standard. And so that's what's applied to the Orion flight software. And that's why you saw such spectacular, consistent results during the Artemis II mission.
We have all the advancements of AI in deep learning, but to me, what you're describing is there has to be some sort of culture at NASA of apprenticeship where you have engineers that speak to younger engineers to say, okay, this is how we do things from a safety perspective. This is how we ship software, because it seems to me that it has to be culturally ingrained, because if you're going to take some of the newer available tools, you could potentially run afoul of the standards. Am I right to think about that there is an apprenticeship program where the individuals that are developing this life and death software?
Yeah, absolutely. There's a great mentorship program. There's a hiring pipeline where college students come in and receive mentors. There's formal mentorship programs as well. But then nobody's ever checks their own homework. Essentially, someone might write the code, but it's going to be reviewed by peers to make sure that the code actually satisfies the requirements and then satisfies the design intent. And then someone else is going to be responsible for actually doing the formal verification of it. So that way, you never have the person who writes the software being responsible for checking the software. You set those up intentionally adversarially. That's a best practice in high criticality software. Oftentimes, you actually have redundancy, and you assume that the software can fail. And so you assume that if this layer of software fails, what's the next worst thing? What's going to catch it? What's going to be the backup? So although everyone's contributions help make the overall thing a success, it's been engineered to not require success on the back of any one particular thing. Usually there's multiple paths to success so that you can have really successful missions.
We're seeing a lot of publicly traded corporations now and earnings. They're disclosing the amount of code their organizations are having written by AI agents or AI bots. Is all the code for the space mission still manually written, or is some of that written by AI bots?
It's a great question. So I left the agency back in 2021. I don't know for the Artemis II mission if any of that was written by AI. I can tell you, I'm sure any code that was written by AI, if it were to be written, would have to go through the exact same stringent processes. Now, one thing that's really powerful is that you can use the AI to help develop all the tests and to do a lot of the things that you have to do to comply with flight software standards. A lot of what I did for a few years could now be dispatched as a Claude, agent task, and instead of having it take me, a few weeks to get it done, you could get the same task done very, very quickly. And then, of course, you have to have human review of it to make sure it's all solid. just as if I had dispatched that task to a teammate. And so you have to still do all that human review, I'm sure. But to me, it's a very exciting prospect that you could have one engineer have their abilities magnified by essentially having teams of people, and they would just be responsible for reviewing all the code that's being produced while still being conformant to the software standards.
The thing I like about it as a proud American, it accelerates space exploration because you can do more with less. As we've seen the ups and downs of NASA budgets over the years, and now with Mr. Ikerson, it's really moving forward very, very quickly. As it moves forward, when developing a software, so if you look at, so from Reentry, for example, so you have a 0.1 degree that you have to achieve. Does that start with, okay, we write the code and then we put it into simulation and then perhaps into some sort of digital testing? What does that look like? Because there's the margin for error is thin, 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 thin.
Yeah, that's right. Yeah, the Orion spacecraft had a very narrow target to try to hit when it was coming back from the moon. And we talk about it in terms of the angle at which it enters the atmosphere. And that had a very, very tight tolerance. Why was it so tight? It's because our ability to predict the aerothermal performance, or essentially the heating during reentry, has improved so much since the 1960s. Now, during the Apollo era, they didn't have the computers to be able to run advanced aerodynamic models that we can run today on our supercomputers. And so because of that uncertainty, they really made the heat shield really, really capable and really, really thick. And that was a deliberate design decision they had because they had so much uncertainty. Today, we have the ability to better model that stuff so we can actually shave that mass out of the vehicle, and that enables more capable exploration missions by essentially having to reduce the margins there so you can carry more mass to do other, or to bring other instruments up into space. And how did we go about actually showing that we could do that reliably? Essentially, we have world simulations where we can simulate the physics of the spacecraft and as well as the uncertainties associated with it. So what is the spacecraft going to do when it fires its thrusters? Nominally, it's supposed to produce this much force, but it could have more or it could have less. The atmosphere varies. The winds vary. The mass and the aerodynamics all vary. There's uncertainty on all of this stuff. And so what NASA does is it runs lots and lots of varied simulations. We call this Monte Carlo simulation. And we simulate lots of different versions of reentry, thousands, millions of versions of reentry, to make sure that despite our ignorance, despite our uncertainty, this system should hold together under any conceivable configuration.
So you're just throwing every possible scenario under the sun and testing it. Is that how we should think about this?
Yeah, roughly. Yeah.
So when it's coming through reentry, we saw the photos of the Artemis, and I got to say, to NASA folks that listen, we know you listen, the photographs of this mission produced were absolutely spectacularly amazing. So please keep the wonderful photographs coming. When the capsule comes down, you could see the burn marks when it landed in the Pacific. How hot does that get on the outside? How hot?
I think it's something like on the order of 5,000 degrees. Don't quote me on that, but it's I know there's NASA media reports of how hot do they expect it to get. It's pretty insane. And so the engineering behind the heat shield design and all the aerodynamics is mind blowing.
NASA engineering is world class. There's no other way to say it. It's world class engineering. I'm curious on the autonomy perspective. If you had to, let's just say, let's ballpark this from a percentage standpoint. What percentage of the Artemis mission would you say was fully autonomous?
Probably 98%. So that the few times that the crew took manual control of the spacecraft to do manual piloting demonstrations, that was the time where there was not an onboard system that was actually controlling the spacecraft. What it is essentially they're inputting different hand control inputs through their joysticks in the cockpit, and that gets sent into a control algorithm, which then fires jets. So it's still part of the autonomy system is firing and still activated. But those are the times when the Artemis astronauts had control of the spacecraft. Otherwise, the autonomy system is in full control the entire time.
Here's a prediction. You're no longer at NASA, so I can ask you for a prediction. When do you predict at some point that we will have fully autonomous space operations?
I would say we are already there. Now, what do you mean by autonomous, I think is the question. Is when you say autonomous, do you mean is there going to be no ground control, no mission control to be monitoring the spacecraft? We already have that today. So deep space missions, there's nobody at the console. Basically, we go have someone check in on the spacecraft, every now and again, and make sure if the spacecraft calls home, yeah, we can go respond to that call for help. But it's not unlike essentially autonomous vehicle deployments where they may be operating without anybody watching, and only if they get in trouble and call for help, that's when then someone, a human in a remote operations center can go and give support. But we already do that mode of operation for deep space spacecraft today. And then for the Artemis mission in particular, it was, mission control was staffed 24/7, just in the event that there's some sort of urgent malfunction or urgent crisis on board the spacecraft. So that way you have the whole team there to support and to provide assistance. So it's not really about, is the onboard system capable? It's really more about risk acceptance. And do you need the ground to help be there to mitigate the risk of the unknown failures that might happen?
Should we think of the ground, not, I'll use the vehicle term, remote operator, but to me, it seems like it's more of a specialized specialist, where if there's an incident with something, NASA has immense resources. You probably have a specialist for, let's just say, bolts or for wires and these different little things. Is that eventually, so eventually it operates fully autonomous, and then there's on the ground specialists in case of an unforeseen, unfortunate incident?
Yeah, that's a great question. The idea is that typically in human spaceflight operations, there's a front control room, and those are essentially the top. What you're seeing is the top of a whole bunch of pyramids, and each pyramid is essentially an entire domain of discipline experts, maybe trajectory experts, life support experts, power and communication experts, all structural experts, heating experts. And so what you're seeing is a huge organization working together to manage all those sorts of things. So that way, if something goes wrong in this heating system, they had some issues with being able to dump overboard some of the urine from the astronauts. That line froze up. I'm sure the mission evaluation room is the back room of engineering experts for that particular area. But I'm sure was pulling a lot of hours trying to generate troubleshooting recommendations to get that issue resolved. So teams on the ground are ready to go resolve those sorts of things. The question is, when are you able to operate without those things? It's probably during kind of quiescent flight where the risk of not getting an immediate response is kind of low. And so in general, for human spaceflight, I expect there to be ground crew there to help provide support to the onboard crew for quite a while.
I know I'm going to go into science fiction here, but I can't help it. When do we get a nice version of Hal in the spacecraft that doesn't go rogue and can do self-healing? When does that come? Because you're seeing what's happening in the development of these models. It seems at some point,
Yeah.
this is hypothetical, NASA could potentially develop their own model that can do self-healing on these spacecraft.
Yeah, you may be surprised that we're a little bit closer to that than you may realize. I don't think you need a full AI agent to be able to do that sort of stuff, but falls under what NASA calls fault detection, isolation, and recovery. So imagine that you have on board the spacecraft redundant navigation systems that are all operating using different sensors. And if one of those sensors goes bad and kind of contaminates that particular system, well, they have a software module that's monitoring and comparing all those things, isolates that out and says, that one's sick, unhealthy. I need to, restart, that IMU or that sensor. I'm going to go restart that computer and self-heal automatically. So for a given depth of failure, the systems today can already isolate and recover from those sorts of system issues. Now, the problem is there's so many possible combinations of simultaneous failures that you can't possibly build a system ahead of time that can cover all these sorts of things. But if you had, like you're saying, Grayson, like a smart onboard system that could understand all the system layouts and how everything works and actually come up with an action plan, that would effectively be like a superhuman replacement that replaces kind of the superhuman intelligence of everyone working together within mission control to solve problems. You could potentially, in the science fiction world, have that same capability all packed into one giant AI model, for instance.
It would seem to me as we go past Mars and go deeper and deeper into space, it's at some point in the future we're going to get there. with human flight that you would need that type of technology. The thing that I've picked up from this conversation is that there's a lot of really great technologies, processes that NASA has developed that can transfer over to the truck side, into the vehicle side. Are you seeing a transfer of even just process or technology that NASA has, I use the term patented, coming over? Because it seems to me that there's this culture of we can't mess this up, we can't mess this up, we can't mess this up. Have you seen that come over to the truck side at all?
Yeah, absolutely. I helped bring that. I'm the cross-pollinating thing that comes from NASA to Kodiak, for instance. And so it's the vigilance, the discipline, and the rigor. So a good example of this at NASA, a lot of risk analyses are done using a technique called probabilistic risk assessment. It's how they assess the risk of things like re-entering debris from dead satellites coming in and striking people on the ground. It's how they assess the risk of where can't the boats and the airplanes be during launch? Because if the rocket were to blow up, where could the debris go? It's a big probabilistic risk assessment. When you see SpaceX launching Starship, sometimes those things don't go great and there's debris coming down. Nobody's getting hurt. Why is that? Because because SpaceX has to submit a probabilistic risk assessment result to the FAA to get a launch license. So what I've done is, I got some exposure to that at NASA, and when I joined Kodiak, we take the probabilistic mathematical framework and we apply it to the problem of behavioral safety, and that's how we estimate at Kodiak our behavioral risk is through a PRA, just like how NASA applies it to all sorts of other problems.
So it seems to me that you're bringing this NASA culture to Kodiak, and you have a great gentleman on your team, Brett Farbia, who leads your law enforcement outreach. Hey, Brett. And you speak to Brett and you ask him all these crazy things about what could happen with the truck. And then I said to him, well, what about this? Well, I've seen it. And it seems that you got something special. If you combine the law enforcement, what they've seen with the NASA stuff is that, I'll use a term that I can use, you're de-risking the deployment. Am I reading into this correctly?
Yeah, I think, if you've never done a safety critical system before, where you are literally betting with someone else's life that it's going to work, yeah, you might not know all the things that you need to think of before you go deploy that system. And so I'm very, very fortunate and blessed to have had that NASA experience to get excellent mentors and learn from some truly talented engineers. I carry that with me at Kodiak. And so it helps us be smart about our risks, but also to not be paralyzed by the risks. The Artemis II crew knew what the risks were of going to the moon, and they chose to do it anyway. Every astronaut who flies to the space station knows what the risk is, and they choose to do it anyway. You don't want to be paralyzed by the risk. You want to take calculated, smart risks that are worth the reward.
Is that where the culture of healthy paranoia comes in that NASA has pioneered?
Yeah, absolutely. In general, when we're assessing the risk of our system, we assume from first principles that we know on the safety side that we know nothing about the performance of the system. And in fact, we have to be overwhelmed by the evidence that this is actually incredibly safe. So we do this mathematically by assuming every possibility is equally likely, that this could be having a collision every single encounter with a pedestrian, or maybe it'll never do it. All of these things are treated as equally likely hypotheses. But we have to run enough tests to convince ourselves that this system is so safe that the residual uncertainty that we have about the risk of it is so small that we can still accept that and continue to launch.
Does that apply for the on-road aspect of your business as well as the Permian? And I'm joining the team this week in the Permian, going with Pete, the famous your famous colleague known as the Bigelow Battle Champion. He was a great moderator for that. We're gonna have a great time out there. How do you plan for those environments? Because what Pete's told me, he said the Permian's hostile. I've watched Landman. I've seen kind of some Hollywood version of the Permian, but it seems that over the road versus the Permian are two completely different operating environments.
Yeah, they are quite different. There's more overlap than I think people realize of like our driverless deployment in the Permian, I think, is awesome for our organization because it forced our entire team to grapple with the fact that, hey, this is no longer an R&D project. This is a real thing with real consequences for getting this wrong. And so forcing the organization to go through that maturation phase, going from iterate really fast and see what happens, to no, seriously, sign your name on the dotted line that this is rock solid. That was an excellent learning process for the organization. So when we're turning our attention now to over the road, we have that muscle memory already built. Yes, the problem's a little bit different, but in terms of establishing the processes that you need to have to guide scalably an organization through these sorts of complex launch decisions and deployment decisions, yeah, we've built that all up, and now we're excited to be able to apply it to over the road.
Would you view the Permian? I know it's a commercial environment. You're very public on that, but I look at it as a learning environment because you operate on some dirt roads. It gets monsoon, so you get potholes. You have big rocks. You have dust. You have all sorts of interesting weather environments there. That to me, it seems that at least it can harden the Kodiak driver for what you might encounter over the road. Because if you look at your very public DFW to Atlanta lane, you're running through some very potential hostile weather environments that occur, especially in the summer.
Yeah, that's right. And so all those sorts of environmental factors can wreak havoc on your ability of our perception system to perceive the world accurately. So what's great about operating out in West Texas is you get exposed to all that sort of stuff. The sensors get dirty. There's rain. There's nighttime. There's dust that's kicked up by every vehicle that drives by. So it gives us a wealth of data to help us assess our system's robustness in all these challenging ODD conditions. And so that gives us the confidence that we are actually thinking about the problem correctly of assessing the risk in the Permian. It helps guide us of how we structure the analysis to make sure that we're taking smart risks and acceptable risks when we go onto the eventual highway.
As we discussed, the environment there in the Permian is hostile. From a safety perspective, how do you prepare and or certify the system to operate in that environment? I was when Don Burnett hosted me at Kodiak for the Signals event, which was a lot of fun. Thanks, Don. He showed me the Permian truck, and this is like Rambo truck. It was all hardened, ready for battle. How do you prepare these trucks for that environment from a safety perspective?
It's not just one solution. There's no one thing you have to do. You have to do a whole bunch of things. We take all those things that we do and we summarize it into our safety case. And that's basically our structured argument of why we think our system is acceptably safe to operate in that particular environment. And you're right, the ODD in the Permian is rough and tumble compared to a highway ODD. Highway is hard for different reasons. And so we structure all that evidence together. So that spans things like safety culture, our safety management system, our engineering processes. How do we know that our code is right? How do we know that it's going to do the right thing in each situation? How does our system degrade when things are malfunctioning? What's our operations team like? Are they safe? Do we hire competent people? What's the training? What's our posture on cybersecurity? What's our vulnerability assessment look like? How are we monitoring our fleet and continuously improving and monitoring the whole thing? We take all of these things together as evidence of why we think our system is acceptably safe. So it involves a lot of functional safety, cybersecurity, SOTIF or safety of the intended function analysis. It takes the entire organization to pull all this evidence together to get ready to actually launch.
And after you launch, this has been well documented in ground vehicle autonomy, you run into edge cases. They're going to happen. How do you prepare for edge cases both in the Permian and over the road?
Yeah, it's a great question. Oftentimes failures at NASA are really due to a lack of limited imagination, close calls, things that people didn't think could happen, or we incorrectly understood what could happen, how badly that could go. So there's a lot of lessons learned there. So there's kind of some degree of humility that you must carry with you because you're probably not as smart as you think you are. So in terms of edge cases, we go out and we drive a lot with drivers in the cab first to kind of understand the environment. And I remember the first time we saw a cowboy out in the Permian. We had heard there were cowboys out here, but we had never seen one. And I had penciled into our risk assessment, well, I'm guessing, without having seen one, that maybe we'll see one every 10,000 miles. Well, we saw one after our first 5,000 miles, so I wasn't too far off as far as an initial guess. But what we do is we essentially catalog the set of all possible scenarios that we can imagine, and then we say, I'm going to pencil in some initial numbers to these things as reasonable engineering guesses. And then we're going to go explore those things through some testing. And we're going to characterize the risk of our system in those extreme scenarios. And then we go off and we operate and we can collect more information. If you see things that you didn't count on happening before, and it shows up in the real world that you didn't anticipate it, that's an opportunity for learning. We take that and we put it back into our risk model. So it's a continuous learning process. You always try to burn down the risks as best you understand them. And sometimes you have to, the most important thing you can do is to go explore into the areas you haven't really considered yet. So we have a very exciting new tool that we're developing called Breakpoint. And Breakpoint allows us to go find these really extreme scenarios, things that we won't see in our normal driving operations, but it allows us to find these critical failure modes that could potentially happen, but just with extremely low probability. And that's how we build our confidence that our system is actually very, very safe.
To me, it's a risk mitigation strategy, and it's a living, breathing document that you're always updating. So you're getting this new data in from your breakpoints, for example. You're putting that into the risk model. So should we think about this from your risk model is always evolving? If I don't know, I'll just give you an example. A tumbleweed goes across the road, for example, or something that goes into the what if risk model, and with the ultimate goal of being able to operate the safest autonomous truck that you can.
That's right. You're battling two things. You're battling your ignorance of what don't you know, and you're battling the known things that are actually dangerous, and making sure that you make sure that those things are actually incredibly safe. So our risk model accounts for both of these factors, essentially our lack of knowledge, as well as the things that we do know about are dangerous and what's the risk posed by those things. We consider all of this stuff, and as we observe new information, run new tests, run new simulations, run more structured tests, we fuse it all together, and that gives us a continuously updated version of our risk profile. And that allows us to make smart choices. You don't have to go and solve every single risk all at once. Oftentimes, most of the risk comes from maybe two or three sources, and everything else maybe constitutes this tiny little sliver. This is the well known Pareto principle. And so you go after and you focus on your dominant risk factors first before worrying about the other things. And you progressively drive down your entire risk profile until you're safe enough to launch.
And then when you're safe enough to launch, you give the team the thumbs up and says, okay, cleared for launch. So that's great. But then what you said, which I really like, you're constantly monitoring this situation. You're monitoring the risk profile, which goes into critical mission engineering. Kelly, what is the future of critical mission engineering, and what role do you see risk playing in it?
I think functional safety will continue to be a part of this. The thing that gets me really excited, though, is reasoning about the risk of behavioral safety. That's really, really hard. Why is it so hard? It's because the number of scenarios that you could potentially encounter is literally infinite, and you can't possibly test in all of these situations. So, how can you intelligently proceed without having explored everything? That's the area that I'm most excited about, and that's what I focus on in my role at Kodiak. I think that's where the most room for maturation within the industry is going to be. And so I think that's where you should expect to see a lot of focus, a lot of research, and a lot of progress there. My conviction is that whoever can solve that problem effectively will be the first to confidently go to market, knowing that they've got this responsibly figured out. You're not just launching haphazardly, ignorant of the true risk. You're doing a deep analysis to make sure that you've thought of all the things ahead of time so that you don't reach market first and then have some sort of catastrophic incident. That is the key trade-off that companies must navigate, is not launching prematurely with risks that are unacceptable, and not launching too late because you simply don't know what the risks are, because then you run out of runway and you no longer have a product to be able to sell. So striking that balance and estimating those risks really well is a key factor for the success of any autonomy company, in my opinion.
It's a fine balance at the end of the day. And when you properly manage the risk and you properly message the risk, you build public trust. And what Kodiak is clearly building is a culture of safety, a culture that understands risk, and a culture that is deploying autonomous trucks safely at scale. The future is bright. The future is autonomous. The future is a robust safety culture. Kelly, thank you so much for coming on the road to autonomy today.